equilibrium. So equilibrium and acids and bases, which is the next chapter, are very tied together, so we're really going to be sort of covering them side by side, almost as if they're one chapter. It's technically broken up into two chapters. Equilibrium is basically a concept that every reaction is actually reversible to some extent. Up till now, we just talked about I mix these two reactants together, and then they make these products, and there's no more reactants, and it's all turned into products. But that's not really quite how it works in chemistry. We dealt with that at the beginning, but the idea is that we now need to understand that all of these reactions are reversible. So if I start with 100 of each reactant, and I'm supposed to get 100 of each product, maybe not all 100 of each reactant reacts. Maybe only some of it reacts. And what that means is that, and when we talk about all these, some of the forward reaction can be occurring, but I can also think about the products can chemically react to make the reactants. We would call that the reverse reaction. So a lot of times we'll sort of talk about this as the forward reaction and the reverse reaction. Now this is technically not a chemical reaction, this is a state change, but it's one we're familiar with, so I'm going to treat it as if it was a chemical reaction. In evaporation, I have liquid water turning into gas water, water vapor, steam. At the same time, of course, water vapor, steam, can turn back into liquid. So I have a reverse reaction going on, and I would use a backwards arrow to indicate that both could be going on. I could also flip it, right, and write it this way with gas on the left, but that's kind of confusing. So typically what we do when we talk about the reverse reaction is we leave the reactant where it was, we leave the product where it was, and we reverse the arrow. Now in reality, if this is going to this, then this is the reactant and this is the product. But just to keep things simple, we're always going to part the ones on the left we're referring to as the reactants, the ones on the right we'll talk about as being the products. So we typically use double arrows. You can see an arrow like this. Sometimes it's a half-barbed arrow where it doesn't have a full arrowhead, it just has half and one going backwards. These are indicating that this is a reaction that is in equilibrium. It's a reversible reaction. So again, by convention, we're going to talk about the things we write on the left. When we see these double arrows, the ones on the left we'll refer to as reactants, the ones on the right we'll refer to as products. So let's see what can happen with some of these. Again, we're going to talk about that forward and backward rate. So the rate at which things combine is different for different reactions. Rust is a very slow process. If you take steel and you put it outside, it doesn't immediately rust. It can take a very long time to react. Others, an acid and a base, are very fast to react. Or I mix the hydrogen and oxygen and get a quick explosion. So some have a very fast reaction rate, and some have a very slow reaction rate. And of course, I have a forward reaction rate and a backwards reaction rate. If we say that all of these reactions are a little bit reversible, all of them are occurring in the forward direction and also a little bit in the reverse direction. So they can change with time. They can be fast or they can be slow. If you have a fast forward reaction and a slow backward reaction, I have a very fast reaction competing with a very slow reaction. I'm going to mostly see products. I'm going to mostly observe the forward reaction. So assuming that I had somebody I had a bunch of Legos, and one person was putting the Legos together in a forward reaction, and another person was pulling them back apart. The person putting them together was very quick, and the one pulling them back apart and putting them back into the unreacted, into the individual Lego pile, you would mostly see a lot of Legos being put together. Very few would be taken apart if that person was slow. If I have a slow forward reaction, the person putting together the Legos was very slow, and the person taking them apart is very fast. You will mostly notice the backward reaction. And sometimes we use different length arrows to sort of say that, okay, this is the faster reaction, this one's the slower reaction. And this can happen at the beginning of a reaction, when I first react them. I can have a different forward reaction rate from a backward reaction rate, which means mostly I'm seeing product being made, or mostly I'm seeing reactants being formed from products. I can make some comparisons of things that aren't really chemical reactions, but kind of make this concept a little bit better. if I thought of two competing processes. This is filling the tank, this one's emptying the tank, dripping out. This would be like the forward rate, and this one is like the backwards rate. The forward rate is obviously I see a lot of liquid going in at a very fast rate, so this is a fast forward rate. And I just see a couple of drops coming out. That would be a slow reverse rate. And somehow these were cycling back up into here. I would know this because I'd see this is filling up. I'm mostly going to be noticing what's happening in this. I'm saying that this is filling up. I might not even know there's a leak. On the other hand, if I had a fast backward reaction and a slow forward reaction, I have just drips coming in, and this is draining out at a very quick rate. What I'm going to see is I'm going to see this tank emptying out. I might not even notice there's any water coming in. So I'm going to mostly be noticing the effects of whichever is the faster reaction. And this is true at the beginning of a reaction. But most of the time when I have a reversible reaction, at some point it reaches equilibrium. And at equilibrium, the forward rate and the backward rate are equal. So that means every time a child would be putting two Legos together, another child would be taking the two apart. So you would never see any change. It's sort of like it stops, the piles would stay the same size. So we could see this, we see this a lot in this, again, water evaporation is not really a chemical reaction, it's a physical change, but I can sort of make a comparison to it. That there's a certain point at which things are stable. In fact, in the air now, there's a certain water vapor amount in the air. I have some water source here. And this is in equilibrium. So I have a bunch of liquid. I also have probably some water vapor in the air above it. So they're in equilibrium. So I'm not seeing anything change. The amount of concentration or products doesn't change anymore. It really hasn't stopped. I still have some forward, I still have some backwards, but it hasn't stopped. But I have a equilibrium now. So for every reversible reaction, it has its own particular point at which it reaches equilibrium. And at that equilibrium is, at the beginning of the reaction, the forward reaction might be fast, or maybe the reverse reaction is fast. But at a certain point when it reaches equilibrium, I don't notice any change anymore because the forward and the backward rates are equal. At equilibrium, there's no longer any concept of rate because nothing is changing. Both rates are equal and there's no change in concentration. We can observe this balance point, and it's different for different reactions and different processes, and we can put numbers to it, but I can't change it necessarily. So, if at some point I reduce the fast reaction to being exactly the same drip rate as this coming out, all of a sudden the tank would remain at a certain level. The level would not change. In this case, it was pretty full when this slowed down, so it looks like I have a mostly full tank. In this reaction, it looks like the backward reaction was going very fast, and now it slowed down to just a drip. But it happened when this was low, so this one has a low level. So in other words, the levels for each chemical reaction might be different. In this case, when it reaches equilibrium, it's a mostly full tank. In this case, when it reached equilibrium, it's a mostly empty tank. And we can compare that to different chemical reactions. Okay, understanding, and again, we really need to understand this concept of equilibrium. If I had people moving from one room in a party to another room in a party, maybe I had 24 people in the first party room and 18 people in the second party room, and 4 people moved from room 1 to room 2, and another 4 people moved from room 2 to room 1. If I were taking pictures, if I was just taking a head count, I wouldn't know that anything is changing. The people are not remaining in the same room. The number of people in the room is not changing. This was 24 before they moved, and it's 24 after. This was 18, it's still 18. But I don't have to have the same number of people in this room as in this room. If I'm thinking of this as a chemical reaction, this might be my reactants, this might be my products. So in this case, I have more reactants when I reach equilibrium than products. So this is sort of